So thanks everybody for this last session of the last day as a non-unconference day. I'm just going to point out that there is going to be an unconference tomorrow. I hope most of you are going to assist it and that we'll have a productive day. But using this time, I'm just going to give you a short update about pgstats, like in 20 minutes very, very quickly. Originally, this was like a 15-minute talk, but so I had to shorten it quite a bit to make it fit into this slot. But let's just dive into it. First, a few words about me. My name is Michael Paquier. I am a PostgreSQL committer, major contributor, committer since 2018. I do PostgreSQL stuff, and I'm currently employed by AWS since 2022 to do PostgreSQL stuff. I review patches, I commit patches, I author patches sometimes, and I've perhaps authored, I don't know, hundreds of patches into PostgreSQL, bug fixes, features, reviews. Large portions of the code tree are stained by my footprints, I would say. And so, as you may have heard already, yes, I am French. I am based in Tokyo, and I've been living in Tokyo for many, many years, a time long enough for an adult to be able to vote. Do the math. Not in the US, but in Europe. Anyway, today I'm going to keep it very short, so it's good if you just remember 10% of what I'm going to say. I'm going to go through the architecture, what we did in 18, and what you can do now using extensions. Anything I am pointing at, this is not what I call a hand-waving talk, when I talk about possibilities or futures. This is in the tree. You can use it today. You can clone the Git repo today, and you can play with it. All the features are in 19 already. Some of them are in 18 already released. So you can already use all that. And except if some of them are reverted, which is very unlikely based on what we did, because, you know, I'm a super confident guy. I'm kidding. I'm like super pessimistic, but I don't think those are really going to be reverted. But so you can already play with them, and I do encourage you to play with them in case there are bugs, such as I can address them. Anyway, regarding pgstats, what's pgstats? It's about statistics. No surprise, I guess. It's a way to give for people at SQL level a view of the various states in PostgreSQL. For many parts of the system, it's a critical thing. You can get an idea about what happens related to objects, be they controlled by DDI, like tables, indexes, functions, executions. More global states, like processes, checkpointer, while data, while receiver, while sender. We have various functions, various views that you can create to get various access into that. And all this activity is centered into a central piece called the cumulative statistics in PostgreSQL that we simply call pgstats. An exception to that, so we have many system views. Those are called pgstats something, except pgstat activity, which is called stat for I don't know what kind of reason, because it gives a dynamic view of the state, but it's like only pgstat activity is really actually not about stats. It's about more the current state of your sessions. So most of the views, we use SQL functions and wrappers around them that act like views. We have docs about them, all of them. You can get a look at that. Of course, we have stuff like transaction SLRU, things like that. Anyway, since PostgreSQL 15, the implementation of PostgreSQL has been heavily re-implemented by mostly two individuals. One of them was doing a talk about profiling a few hours ago in this room called Andres Front, who committed the patch. And the main author of moving pgstats into shared memory is a Japanese guy from NTT called Kyotaro Horiguchi. The moving to pgstats into shared memory had many goals. The main one was scalability, because before we relied on synchronous pipes to be able to transfer the data between all the backends and a stats collector that we have, which was a dedicated process used to aggregate the statistics. Now we have everything in shared memory. We don't have any more a process. This is coming with advantages and disadvantages. I did mention previously that stats are critical for some parts of the system. One of them is auto vacuum. We use the stats at table level to decide if a table should be auto vacuum or auto analyzed. And coming to the first point, the current architecture that we do have means that the durability is guaranteed by on-disk data. We load it at startup. We flush it at shutdown, meaning that during the runtime, as long as you do not restart PostgreSQL, all the data never touches disk. When the data is loaded at startup, we remove the file which is on disk. If you crash, you lose the stats. If you crash, you make auto vacuum, giving up on tables as long as we do not have any kind of stats. If auto vacuum does not see any stats at table level, it just gives up on the table. It will not auto vacuum it. So you either need to run it manually once again, or you need stats fresh enough after, I don't know, steady workload to be able to say to auto vacuum that it actually needs to do something on the table. So that's part of the new architecture, one of the limitations. One of my colleagues called Bertrand Rouveau, who is, raise your hand. I mean, he's not, oh, he's there in the back. He has been working on this issue. We may be able to address that for 20, but we still need some work in this area. Anyway, for statistics, I have been talking about various types of stats, and roughly we have two types of statistics. One is called variable sized, which is based on an object basis. For example, when you create a table, when you create a function, you don't know how many functions you are going to have, but those are bounded by the DDLs you run, by your schema itself. Those are variable sized, meaning that we don't exactly know the number of objects, but we want to store data about all of them, and we want to have each stats data associated to each object itself. The second type is fixed size, which is kind of an implementation basis. We use a chunk of shared memory which is fixed, and this is used for state data that we know will never change over time. An example of that, the statistics about the checkpointer. We know that all the fields are known. So we basically allocate a chunk of memory at startup and just rely on that and use it. Each stat is called a stat kind. For example, we have a stat kind for tables, for relations. These include table indexes, for functions, for replication slots, for checkpointer, while SLRU, and we have, I think, 14 stats kinds. Anyway, so this implementation, this re-architecture of pgstats happened in this commit that was in 15. On the source code basis, we have things that are kind of nicely split. The core parts are called pgstat.c that handles the main parts of the code. So if you want, for example, to contribute, look at this code. I recommend you to look at the three lines that you have. pgstat.c is about the main, I would say, APIs, the ones that, for example, read the stats on disk, write it back. We have also a few APIs in it to handle stats kinds. There is a part about the shared memory, which is in pgstat underscore shmem.c. Perhaps shmem sounds weird, but it's a pgstat shmem. Sorry, I use shmem because it's written shmem. Shmem is weird?
No, it's awesome. It's totally shmem.
It's shmem.c, right? .c, which is about the shared memory part of it. And we have also two headers which are kind of important, which are called pgstat internal.h and pgstat.h. Those two ones, particularly the first one, defines a set of callbacks that can be used for each stat kind to define different properties. We have a stat kind. Those can register callbacks that are statically stored in pgstat.c. And you can define on a function basis what a stat kind should do. We have on top of that one file for each stat kind where those callbacks are located. For example, we have pgstat database.c, but we have also pgstat underscore archiver.c, checkpointer, while.c. We have all those files split between each other. All those files are under src backend utils activity. So anything related to stats would be in this repository. If you are looking for a stats kind in itself, you will need to look at a given file to try to understand how we handle stats and how internally we do things for those stats kind. So about the fixed sized stats, those are simply allocated in a chunk of shared memory sized at startup. This does not change. If you need to do concurrency control over those stats, how they are updated, if you look at each stats kind, we basically use lightweight locks, such as we make sure that when a backend updates those counters, when we have another backend that queries the functions or the views that look at those counters, we don't have anything in terms of shared or even exclusive locks. So it's a concurrency protection based on the fact that PostgreSQL still uses processes because everybody likes processes and not threads. But we have a set of structures that are separated that track the data that we have in shared memory, as well as the data that we are ready to flush, for example, when we commit. One property that I have not, I think, written on the slides of this shortened version is that the stats currently are updated during the transaction and they are flushed into shared memory when we commit a transaction. This allows us to limit the number of interactions that we have with shared memory, such as even if you have, unfortunately, a cost of that is that if you have a very long transaction, you will only see the data updated, particularly for analytical data, once the transaction is committed itself. You can get, so this is due to the infrastructure that we have. For the fixed size kinds, we have data located for a fixed size for a while. View, which is very, very useful, is called pgstat.io, that gives you data about I/O activity. And we have also slru, which is an internal thing of Postgres for exact, multi-exact, and things like that. So the second type is variable-sized stats, which refer to sets of objects that are defined depending on the object type we have. These are stored in a shared memory hash table. They use a key set of data based on the stats kind, the database OID where they are stored, as well as an 8-byte OID, which is basically using the 4-byte OID when you create an object. It was a 4-byte OID directly in between 15 and 17. This has been enlarged to be 8 bytes in 18 for reasons I may be able to speak to you about in a few slides. These refer to database, tables, functions, anything which is DDL related. The locking is internal, handled inside the the dynamic shared memory hash table. Where we have a set of partitions inside it. So there is nothing related to locking for those stats kinds. This is internal to the dshash.c, which is the internal implementation of PostgreSQL that we use as API layer for having hash tables in shared memory. The maximum number of objects that you can have is not capped naturally. But you can, it's basically naturally controlled by the DDL you use. Regarding the reporting, we limit that depending on the DDL that we have. As I mentioned previously, we use a set of pending stats that are updated within each backend, and those local data are then flushed when we commit the transactions. The save data is in a shared memory, is in a memory context, in top memory context. And we have also a call called a very specific API called pgstat report stats that's called a transaction commit and can be used to force stats to be flushed even or not on a periodic basis. That we use, for example, in while senders, while receivers, or even the context of checkpointer or dedicated processes, of course. But that's where the stats are getting committed most of the time. I mean, all the time, basically. It's the only entry point. About Postgres 18, we have a new set of APIs called backend statistics that have been implemented by Bertrand, who is behind, that offer you statistics at backend level as long as the backend is alive. This is able to give you information about the states and how the activity is balanced. For example, while and IO for each backend that you can do. This is in pgstat backend.c. And we have functions that can be joined with pgstat activity, such as you can get a view of the while of the IO activity when you run, for example, benchmarks. You could, for example, use that to detect while spikes, IO spikes. It's the same layer as pgstat IO and pgstat while, except that those functions can be used with a PID input to get a set of data, a set of rows for a given backend. There are also examples of stats in the rock. Something that has been implemented by somebody from Microsoft called Nazir Bilal Hayuz, sorry if I didn't pronounce it well, and I'm not sure if you're in this room, is improvements to pgstat IO, where now we do not count the data based on the block size, we count them based on the bytes. The advantage of that is that now pgstat IO has been extended to track while data, such as you can track the amount of bytes that have been used to initialize while segments, as well as the read of the while segments and the amount of write activity that you do have. I don't think I have a lot of time, so I'm just going to speed up a little bit. Sorry about that. Regarding pgstat database, we have in 18 parallel worker activity, where you can get counters about the number of parallel workers that have been planned by the planner and the number of workers that have been actually executed by the executor. We have the same information, pgstat statements as well, for each query as well. So, yeah, so I have actually 2 minutes to talk to you about extensions. I need to be short, but the idea is that I have worked for a patch for 19 to allow people to use pgstats in extensions. You can use the same APIs, the same facilities. You can define fixed size data, variable size data. You just need to register it using SharedWheel library, like you would do for a custom resource manager using while. And they need to use a fixed ID for the stat kind that you assign close to it. I know that some people have been using that. You can reuse the same APIs as the core PostgreSQL to do so. So about the stats kind, so we have ranges for them, and for the custom kind, we have also a custom range that you can use when you register each one of these. About the source code, we have templates, and you can also use a specific ID when you want to implement something, which is called pgstat kind experimental. You can also reserve an ID on the PostgreSQL wiki to organize things, such as open source extensions can we can organize the concurrency of the custom stats, and there is an API to register your kind. The pgstat kind info is a set of callbacks. It's the structure used by in-core stats kinds as well to define a set of callbacks that would be pointers to the functions that we use for the other in-core stats kinds as well, but at custom level in the extensions. I have a few things about the callbacks which are not that interesting. Callback, I'm going to split that. This is perhaps the important part. It's about the template. We do have templates in the source code itself that you can refer to use as example for variable size kinds as well as fixed sized kinds. If you want to implement your own thing, your own extension to be able to reuse those statistics, I do invite you to look at that. And the last thing that I wanted to mention is the reason why we have been doing that. There has been debate in the community about moving pgstat statements into core, which may or may not make sense. But the idea is to be able to reuse all of that, everything we've done in 19, and have pgstat statements able to reuse the same in-core pgstats. The idea behind that is to make it scalable, because pgstat statements does not scale well at with many cores and high-end machines. And we have other issues with it. For example, it's text file. Our idea is to rely on the pgstats internal that we have and make it actually scalable and usable by many users. Sami, who is there, has been working on a patch to do this move. We have all the basic infrastructure in kernel, such as you could even do it as an extension at this stage. I think it's everything I have. It was super short. We do not have time for questions.